To know how effective a teacher actually is, standing at the front of a classroom and watching them work won't give you the answer. To accurately judge instructional quality, we have to look entirely at the consequences that instruction has on student learning. This requires separating two concepts that are often conflated: grading and evaluation. Grading is an appraisal of the student. Evaluation is an appraisal of the teacher's instructional program. These two metrics can diverge entirely. A teacher might award a student an A because the student easily grasped the concepts, even if the instructional program itself was deeply confusing and ineffective for the rest of the room. To measure this objectively, we apply an ends-means model. The ends are the specific curricular aims the teacher intends to reach. The means are the instructional activities the teacher deploys to achieve those ends. Post-instruction assessment provides the data link between the two. Valid evaluation relies on gathering objective evidence to prove whether the instructional means actually produced the intended curricular ends. Testing students only after instruction concludes leaves a major gap in the data. The students might have mastered the material before the class even started. The standard industry solution is the classic pre-test to post-test timeline. Assess the students before teaching, assess them after, and attribute any difference to the instruction. This introduces an error known as pre-test reactivity. Administering a pre-test signals to the students exactly what is important, causing them to behave atypically during the lessons. This animated chart shows another constraint: ceiling effects. If you are assigned a cohort of high-scoring students who hit 95% on the pre-test, there is almost no mathematical room left to demonstrate instructional growth. On the other end of the spectrum, if a cohort scores extremely poorly on a pre-test, statistical probability ensures they will often score higher on the post-test purely by chance. This artifact is known as regression to the mean. Attempting to fix this by using two different test forms rarely works. Busy educators lack the resources to create two perfectly equal test forms. If the post-test happens to be slightly easier, it generates a false positive of brilliant teaching. If the post-test is harder, it creates a false negative, suggesting the student somehow unlearned the material. The standard pre-test to post-test model generates so much statistical noise that isolating genuine instructional impact becomes nearly impossible. There is a data-gathering architecture engineered to mathematically bypass these statistical flaws. It is called the split-and-switch design. To maintain statistical viability, this protocol requires a reasonably large sample size, typically a class of 25 or more students. This diagram outlines the protocol. The first step is to physically divide the classroom into two halves. You divide the roster into two roughly equal groups. A simple method is splitting them alphabetically by last name, assigning A through L to one half and M through Z to the other. Next, you select a specific, high-level cognitive outcome to assess and prepare two test forms, Form 1 and Form 2. The major advantage here is that while the two forms must cover the same concepts, they don't need to be perfectly equal in difficulty. During the pre-test phase, half Class A takes Form 1 and half Class B takes Form 2. Then comes a critical lockdown rule. Students write their names on the back, and the tests are coded so you know they are pre-tests, but they must remain completely unscored. This setup captures two parallel baseline measurements without contaminating the teacher's subjective perception of individual students before instruction begins. Focusing on the center block of this diagram, the instructional phase serves as the independent variable. Following the crossing arrows to the end of instruction, the switch happens. Half Class A receives Form 2 as their post-test, and half Class B receives Form 1. This structural swap neutralizes pre-test reactivity. No student sees a test form they have ever encountered before. With the post-test complete, you enter the physical data pooling phase. Every test copied of Form 1, pre-tests and post-tests, is mixed together into a single pile. The same is done for Form 2. These shuffled tests undergo a double-blind scoring process. The grader evaluates the answers without knowing if they were written before or after instruction. Utilizing nonpartisan scores like other teachers or parent volunteers guarantees absolute evaluation neutrality. Once everything is graded, the hidden codes are used to separate the fully scored papers back into their respective pre-test and post-test piles. The pre to post comparisons are now perfectly aligned. You compare the Form 1 pre-tests against the Form 1 post-tests and the Form 2 pre-tests against the Form 2 post-tests. Because identical forms are compared against themselves, differential test difficulty is completely erased from the equation. The split and switch protocol acts as a statistical centrifuge. It spins out form bias and reactivity, leaving behind the pure, isolated signal of instructional impact. Moving from the classroom to macro policy, school administrators often bypass teacher-made tests, preferring to evaluate instructional success using external accountability exams. The administrative logic is straightforward. If state test scores rise, the teacher is effective. If scores stall or fall, public outcry follows and demands termination. This flowchart illustrates the argument, but the entire model hinges on a structural prerequisite found at Step 3, instructional sensitivity. Instructional sensitivity is a test's mechanical capability to accurately differentiate between well-taught and poorly taught students. Many state-mandated accountability tests are seriously flawed in this specific area. They lack the sensitivity required to measure actual instructional quality. Using these insensitive tools to evaluate employment places immense pressure on teachers. It incentivizes negatively teaching to the test, where the focus narrows to answering specific items correctly rather than achieving broad domain mastery. Using an instructionally insensitive test to evaluate a teacher is like trying to measure distance with a thermometer. The tool simply cannot perform the task it is being asked to do. There is a final blind spot present in all data-gathering models, whether they are built internally or mandated by the state: the unintended side effects of instruction. A teacher's split and switch classroom data and state standardized test scores might both be spectacular, but if the methodology used to achieve those scores was destructive, the evaluation is incomplete. Consider a highly successful math class that drives up test scores, but inadvertently instills a severe, permanent aversion to mathematics in every student who takes it. Or a hyper-demanding instructional style that produces top-tier exam results while simultaneously causing a massive spike in student dropouts. Tracking these side effects requires looking beyond the test forms. Evaluators have to pull from alternative data sources, like attendance records and anonymous student surveys. True instructional evaluation is never passive observation. It is a rigorous accounting of both the achieved curricular ends and the human cost of the instructional means.